Now let's see numerical characteristics of random variable. These are the moments, expectation, variance, row moments, central moments, quantiles, and so on and so forth. So we'll start with expectation with moments. For discrete random variable, the expectation is the weighted average of realizations where weights are the probabilities. So it is actually x1 p1 plus x2 p2 plus xm pn. If you have continuous random variable, the expectation is the integral of x times the density f of x times the differential dx. This expectation generalizes to any function. In particular, for the power function, you have the kth, so-called row moment, expectation of x to the kth power. That one is the weighted average of xi to the kth power, but weights are p1, p2, pn, and so on and so forth. For the continuous random variable, you have also the integral, but now from x to the kth power, density f of x dx. The expectation of general function, not necessarily power as for the moment, is simply the function applied to realizations. In this case, function is phi, and it will be phi x1, phi x2, phi xn, and then you take the weighted average, again with probabilities of x1, x2, xn, p1, p2, pn. Of course, in these weighted averages for discrete random variables, the weights sum up to 1 because they are probabilities, and they all sum up to 1. So you have bona fide mixture, bona fide weighted average. For the continuous random variable, the expectation of the phi of x is simply integral of the phi of x, f of x dx. The variance, standard deviation, are coming from the moments. Variance is so-called central moment. You take the random variable x, subtract the expectation, you center that x around the expectation, square it, and then take expectation again. So it is second central moment. If you do algebra on this, you square this x minus c of x, and you do algebra, it ends up to be the second moment, the second row moment, minus the first moment squared. So the variance is the second row moment, e of x squared, minus e of x, the quantity squared. These two are not the same. The second moment, this is expectation of the square, and it is not the same as the expectation of x, the quantity squared, because the expectation in this case is Jensen's inequality causes that expectation of x squared is bigger than expectation of x, the quantity squared, and that renders variance always positive. The variance is equal to 0 if random variable x is a constant, but if variable x is not constant, the variance is always positive. The square root of variance is the standard deviation, and sometimes denoted by sigma only. So let's take a look at our old friend exponential distribution with parameter lambda. Lambda is rate parameter. Then you can show that variance of x is 1 over lambda squared, and the standard deviation is 1 over lambda. Other numerical characteristics of random variables are quantiles. They're very, very important. We would say that this xi sub p is pth quantile if the distribution evaluated at xi sub p is equal to p. So if we plot this, and if this is CDF, f of x, this would be 1, and this would be xi sub p, then that xi sub p is having the value p, so f of xi sub p is equal to p. Well, this is in terms of CDF. If you think about in terms of the density, the xp would cut the area left of the point, left of the xp, of the value p. So the p area would be left of the point cp. That is expressed by this expression here. And for discrete random variable, you would have actually accumulation of discrete random variables. So it would be the smallest x for which this sum of the probabilities is bigger or equal than fixed p. So remember, in this case, p is given, and then you find cp, which would be your quantile, pth quantile. For example, if you have exponential distribution, and we just mentioned that CDF for exponential distribution is 1 minus e to the minus lambda x. lambda is rate parameter, then you can essentially solve equation f of xcp equals p if you plug in xcp to the CDF and solve it with respect to xcp. You get that the quantile xcp is negative 1 over lambda log of 1 minus p. Log is natural for basis E. So what you have here, you have the following situation. The exponential density, this is p, but xcp is equal to this point here. That point here cuts the p area left in this density, exponential density. The median is a special quantile. It is 1/2 quantile or 50th percentile of distribution. It simply divides the distribution to proportion 50-50. If we are going to plot this, if you have 50% on the left-hand side, 50% on the right-hand side, it is cut by median here. There are other two quantiles, Q1 and Q3. These are quartiles, and essentially they are 25% here, 25% here, 25% in here, and 25% in here. They are cut by Q1 and Q3. So the Q1, median, and Q3 divide the area under the density to 1/4 sizes. The mode is the most frequent, most likely value. The mode is essentially the maximum of the continuous random density, the value that maximizes the density. And if you have discrete random variable, the mode would be the realizations which maximizes the probability. So these are three measures that we saw with random variables. They are called location measures. The mean that we just reviewed, the median is location measure, and also the mode is location measure. If we return back to the exponential distribution with parameter lambda, the median is log for basis E of 2 divided by lambda. The mode is equal to 0. So if you're going to show this, if you have exponential distribution, then this log 2 over lambda would divide this distribution to 50-50 ratio, and the mode is equal to 0 because this is maximizing the exponential density.